In the last lecture, we talked about the development of quantum mechanics, focusing on some of the weirder aspects of this theory. By the late 1920s, Einstein had come to reject many of the conclusions that were being reached by most of the other physicists that have been working on this theory, including Niels Bohr, Max Born, and Werner Heisenberg. A consensus was forming around what would become known as the Copenhagen interpretation of quantum mechanics. According to this interpretation, quantum mechanics is not deterministic, meaning that the future behavior of the universe cannot be reliably predicted, even in principle. Instead, quantum mechanics was a strictly probabilistic theory. And this was something that deeply bothered Einstein. As Einstein liked to put it, he was very reluctant to accept that God would play dice with the universe. But it wasn't only the role of chance and probability in the Copenhagen view that bothered Einstein. He was also very uncomfortable with the way that a given particle could be in multiple places at once, or could be moving with multiple speeds, all simultaneously. After years of debate and consideration, Einstein ultimately came to take and insist upon a philosophical position known as scientific realism. As Einstein saw it, one is a scientific realist if they believe in the existence of a real and well-defined state of the world, and that world exists independently of any observations you might make of it. In other words, the world is a real and well-defined thing that exists independently of us. By observing it, we can learn things about the world, but our observations don't make the world what it is. Einstein's insistence on scientific realism fell in stark contrast to the Copenhagen interpretation of quantum mechanics. According to the Copenhagen interpretation, an electron could be in multiple places at one time. But when an observation is made of an electron, its wave function collapses and it transforms, no longer being in multiple places, but instead being in only one. This interpretation was not compatible with Einstein's ideas about the world, or his adherence to scientific realism. In the years after the Solvay conference, Einstein continued to try to poke holes in quantum mechanics, or at least in the Copenhagen interpretation of this theory. During this period of time, however, it became only more clear that the predictions being made with the equations of quantum mechanics were in very good agreement with any number of laboratory measurements and tests. Quantum mechanics did not seem to be simply wrong. So rather than trying to demonstrate that quantum mechanics is wrong, Einstein instead focused his efforts on trying to show that this theory, as it was currently constructed, was somehow incomplete. Einstein hoped that he would be able to find a more complete version of quantum mechanics that was deterministic and that was compatible with a scientific realism viewpoint. During this period of time, Einstein managed to find and raise plenty of philosophical objections to the Copenhagen view of quantum mechanics. But these objections were, for the most part, pretty subjective, and ultimately they didn't do much to persuade other physicists that the consensus view of the quantum theory was incorrect or incomplete. If he wanted to convince his colleagues that there was really something wrong with the Copenhagen view, Einstein would have to expose something like a logical inconsistency, or identify some other major problem that would be recognized as a fatal flaw. He spent most of the next decade scrutinizing the quantum theory, searching for a major problem that he could expose. And eventually, in 1935, Einstein became convinced that he had finally found such a problem. As early as the late 1920s, Einstein had started to think about groups of particles with wave functions that depend directly on one another. Today, we say that such wave functions are entangled with each other, although that language hadn't been coined yet at the time. Although it would take years before Einstein would fully explore the implications of quantum entanglement, he seems to have recognized fairly early on that this was an inevitable consequence of the Copenhagen interpretation of quantum mechanics. And he also seems to have appreciated that some particularly strange behavior could result from quantum entanglement. In 1933, Einstein fled Nazi Germany and immigrated to the United States, where he took a position at Princeton's Institute for Advanced Study. There he started to work with two other physicists, Boris Podolsky and Nathan Rosen. Over the next 2 years, Einstein, Podolsky, and Rosen wrote an influential article entitled, "Can a Quantum Mechanical Description of Physical Reality Be Considered Complete?" This paper contained the first description of what would become known as the EPR paradox, short for the names of the authors, Einstein, Podolsky, and Rosen. To Einstein, the EPR paradox clearly demonstrated why the Copenhagen interpretation must be an incomplete way of thinking about quantum mechanics. As we'll see, however, Einstein was not entirely correct in this assessment. The EPR paper described a hypothetical experiment intended to demonstrate to the reader what Einstein saw as the paradoxical consequences of the Copenhagen interpretation. Einstein was fond of thought experiments such as this, and the EPR experiment was one of his most famous thought experiments. A number of different versions of the EPR thought experiment have been discussed and proposed over the years, but they all have the same basic elements, including a pair of particles that start out near each other and interact, and then travel far away from each other in different directions. In my opinion, the version that was described in the original EPR paper isn't quite as clear or as easy to describe as some of the later versions. So I'm going to take the liberty of describing to you a later version of the EPR experiment. This substitution won't change any of the conclusions, but it will make things easier for me to talk about. I'm pretty sure that Einstein himself would have approved. The version of the EPR experiment that I'm going to describe to you starts with an atom that is about to decay. When this kind of atom decays, it produces two particles with the same mass. Since the system starts with no momentum, the law of conservation of momentum says that the total momentum of the two particles will have to add up to zero. This means that when these two particles travel away from each other, they have to do it in the opposite direction and with equal speeds. But these are quantum particles, so they don't have uniquely defined values for their velocities. Instead, they are described by a wave function that can be used to calculate the probability that they will be found to have a particular velocity when measured. But before any measurement is conducted, the velocities of these particles have multiple values, and all at the same time. Imagine that these particles travel some significant distance away from the atom, and as they do so, they become increasingly separated from each other. Then after they are separated, you make a measurement of the speed of one of the particles. Let's say, for example, that you measure the particle to be traveling at a speed of 100 miles per hour. According to the Copenhagen interpretation, by making this measurement, you collapse the particle's wave function. But as Einstein and his co-authors pointed out, you seem to have done something else as well. And this is the main point of the EPR experiment. Because momentum is always conserved, by measuring the speed of one of the particles, you also learn the speed of the other particle as well. After all, as I said before, the two particles have to be moving at equal speeds. So by measuring the speed of one of the particles, you don't only cause that particle's wave function to collapse, you also collapse the other particle's wave function as well. And you do this without getting anywhere near the second particle. You've somehow forced its wave function to collapse. Einstein thought that this kind of behavior was patently impossible. He argued that there is nothing one can do to a particle at one location that could possibly affect a different particle at a different location. And the EPR experiment shows that this kind of thing has to happen according to the Copenhagen view of quantum mechanics. This objection is at the essence of the EPR paradox. And with it, Einstein thought he had finally shown why the Copenhagen view had to be incomplete or maybe even wrong. The news media responded enthusiastically to the EPR paper. An article appeared in the New York Times, for example, with the headline, "Einstein Attacks Quantum Theory." Before the EPR paper, the scientific debate over the interpretation of quantum mechanics had largely taken place out of the view of the public, in letters and in discussions at conferences. But articles such as this brought Einstein's objections into the full view of the public. This agitated and frustrated many of the physicists who had been working on the development of the quantum theory. First of all, for the most part, they did not agree with Einstein's conclusions. And regardless of what they thought about Einstein's opinions, they wished he would not air them quite so publicly. For example, shortly after receiving word of the EPR paper, Wolfgang Pauli wrote to Werner Heisenberg saying Einstein has once again expressed himself publicly on quantum mechanics. As is well known, it is a catastrophe every time this happens. Perhaps more than anyone else, Niels Bohr felt that it was his responsibility to respond to Einstein's attack and to clarify and perhaps correct the situation. By all accounts, Bohr was deeply upset and frustrated by Einstein's new paper. Bohr was convinced that quantum mechanics was a valid theory, and he feared that Einstein's attacks would unfairly diminish its credibility. So Bohr put everything else to the side and spent 6 intense weeks formulating and writing a response to the EPR paper and his criticisms of the Copenhagen view of quantum mechanics. The paper Bohr wrote was published in the same journal that the EPR paper had been published in only weeks before, the Physical Review. And Bohr even chose a title for his paper that was identical to that of Einstein's paper. Can a quantum mechanical description of physical reality be considered complete? The difference was that Bohr intended to convince his readers that the answer to this question was yes. In his article responding to the EPR paper, Bohr did not try to challenge the conclusion that the Copenhagen interpretation leads to the entanglement of wave functions. It does. This much was clear. Instead, Bohr argued that there was nothing logically inconsistent with entanglement. Entanglement is weird, for sure, but that doesn't mean that it's not also real. One of the grounds on which one might object to quantum entanglement is that it seems to involve faster than light travel. And according to relativity, nothing can move through space faster than the speed of light. This apparent problem comes from the fact that when one measures the velocity of one of the particles in the EPR experiment, it instantaneously collapses the wave function of both of the particles. Given that a significant distance separates these two particles, this seems to require instantaneous travel through space. Einstein referred to this as spooky action at a distance, and it seemed to violate a central tenet of relativity. But upon closer scrutiny, this turns out not to be the case. It turns out that quantum entanglement might seem to violate relativity, but in reality it doesn't. More specifically, it doesn't enable any particle or any other form of information to move between two locations at a speed faster than light. Two particles may be linked together through entanglement, but this could never be used to send a signal or an object from one place to another at a speed faster than the speed of light. Bohr had shown that a closer look at the EPR paradox revealed that there was really no paradox there at all. Although Bohr's response did little to change the mind of Einstein, most physicists seem to have found his rebuttal to be convincing. Today, the EPR paper is widely viewed as a misstep by Einstein. The EPR paper was important in that it brought attention to the phenomena of quantum entanglement. But it did not ultimately provide a valid case against the Copenhagen view of quantum mechanics. With the EPR paper, Einstein had hoped to deliver a fatal blow to the consensus view of quantum mechanics. But the theory survived and stronger than ever before. Not all physicists, however, were entirely dismissive of Einstein and his objections to the Copenhagen interpretation. Erwin Schrödinger in particular was rather sympathetic to Einstein's view. Although Schrödinger didn't come out nearly as forcefully against the Copenhagen interpretation as Einstein did, he did find the new consensus view to be problematic from a philosophical and conceptual standpoint. Over the years, Schrödinger and Einstein often exchanged letters in which they expressed their mutual discomfort with the consensus view of the quantum theory. As they saw it, the theory they both did so much to create still had lingering problems. And although Schrödinger perhaps did not feel as strongly as Einstein did about this, he too thought that the theory was likely to be incomplete in some important and fundamental way. In November of 1935, a few months after the EPR paper, Schrödinger wrote and published an essay in which he introduced what is known as Schrödinger's cat. You may have heard of this. It's probably the single most famous illustration of just how weird quantum mechanics can be. In his essay, Schrödinger described a hypothetical apparatus designed to illustrate and even exaggerate some of the stranger consequences of the Copenhagen view of quantum mechanics. Let me describe this apparatus to you. You start with a radioactive substance, which has a half-life of an hour. Because of the probabilistic nature of quantum mechanics, you can't predict when or whether the substance will decay. You can only say that there's a 50-50 chance that it will decay sometime within an hour's time. You then attach the unstable atomic substance to a Geiger counter. If the substance decays, it will be detected by the Geiger counter, which will cause a hammer to swing, shattering a flask of potent acid. Lastly, you place this machine, along with a healthy cat, inside of an impenetrable chamber. You then seal the door of the chamber, and you wait. This apparatus might seem complicated, but all that really matters is that if the radioactive substance decays, the acid will kill the cat. And if the radioactive substance does not decay, the cat will remain alive. Now let's consider how to think about Schrödinger's apparatus and his cat within the context of the Copenhagen interpretation of quantum mechanics. Once you seal the door of the chamber, you can't tell whether the radioactive substance has or has not decayed, and therefore you can't tell whether the cat is alive or dead. But according to the Copenhagen interpretation, this is not merely a matter of our ignorance. The radioactive substance is in a state that is a combination of both decayed and not decayed, and therefore the cat is simultaneously both dead and alive. Think back to the last lecture, where we used an example of an electron that is described by a wave function that extends across locations A and B. Until we measure the electron's location, it's in both location A and location B at the same time. A physicist would say that the wave function of this electron is in a superposition of location A and location B. Well, in the case of Schrödinger's apparatus, the wave function of the radioactive substance is in a superposition of decayed and not decayed states. And therefore, the wave function of the cat is also in a superposition of dead and alive states. Only when you open the box and observe the cat does its wave function collapse, causing it to take on a uniquely alive or uniquely dead state. Just to drive this important point home, let me repeat the central message of this thought experiment. Until the door of the chamber is opened, the cat in this example is not only dead or only alive. And it's not just a matter of us not knowing whether it's alive or dead. The cat is simultaneously dead and alive. As I see it, the real power of Schrödinger's cat is that it takes the quantum weirdness of the subatomic world and shows us how these effects could potentially be manifest in something more macroscopic and tangible, a cat in this case. We might be able to accept that electrons, photons, and other quantum particles could exist in multiple states at once, but it's much more difficult to think that this could somehow be true for something like a cat. For most of us, our intuition tells us to insist that the cat must be either alive or dead at any given moment of time. But according to the Copenhagen interpretation, the cat in Schrödinger's apparatus is not. Instead, until it is observed, the cat is in a superposition of alive and dead states. It is not alive or dead, it is simultaneously both alive and dead. When our intuition tells us to insist that the cat must be uniquely alive or uniquely dead at any given moment, it is really just insisting on a form of scientific realism, just as Einstein would have advocated for. In this view, there is a real and well-defined world out there. In such a world, cats are either alive or dead, and cats are never both alive and dead at the same time. But regardless of what our intuitions might say, there is no real evidence that the world has to work this way. It is entirely possible that the world does not choose to adhere to the tenets of scientific realism. This is essentially what Bohr, Born, and Heisenberg were all arguing. And I don't think either Einstein or Schrödinger showed them to be wrong in this respect. But Schrödinger's cat does raise what I think is perhaps a valid objection to the Copenhagen interpretation. In the Copenhagen view, the wave function of an object collapses when it is observed. But this raises the question of what exactly constitutes an observer, and what exactly constitutes an observation. In the example of Schrödinger's cat, we say that the wave function collapses when we open the door to the chamber and observe the cat. But what if there's a flea on the cat? Could it also cause the wave function to collapse? And what is so special about an observer that causes the physical transformation to transform into a collapsed state? It can't be just any kind of interaction, as experiments have repeatedly shown that quantum particles can interact among each other without their wave functions collapsing. In the Copenhagen view, there's something strangely special about the act of observation. To many physicists, including myself, this seems to be a deeply problematic issue, and it leaves many of us skeptical about the Copenhagen interpretation of quantum mechanics. Okay, so at this point in the lecture, I want to step away from the issues raised by the EPR paradox and by Schrödinger's cat, and instead turn our attention towards some of the alternatives to the Copenhagen interpretation that have been proposed over the years. The first of these alternatives that I'll talk about is the class of theories that Einstein had in mind. These are called hidden variable theories, and I mentioned them briefly in the previous lecture. According to the hidden variable theories of quantum mechanics, the wave function that we've been discussing is generally incomplete, and it provides only a partial description of a given particle or system. The missing information, if it were somehow known, would allow one to calculate the state of a system at any given point in time, without any indeterminism or any uncertainty. And furthermore, there'd be no superposition of states. In a hidden variable theory, there is no situation in which a cat is both alive or dead. With the full and complete body of information, you could work out whether any given cat is alive or dead at each moment in time. For decades, some physicists, including Einstein, thought that one day the Copenhagen view of quantum mechanics would be replaced by a more complete hidden variable theory. But little progress was made in this direction. Many physicists tried to develop such theories, but nothing ever worked. Still, some hope that such a theory might one day be discovered. But this all changed in 1964, almost a full decade after Einstein's death. It was in that year that the physicist John Bell wrote a paper in which he proposed a way in which all possible hidden variable theories could be put to the test, or at least all such theories that don't involve faster-than-light travel. This result, which is known as Bell's theorem or sometimes as Bell's inequality, pertains to experiments involving quantum entanglement. In his paper, Bell showed that if there really were a more complete form of quantum mechanics that underlies reality, then certain combinations of observable quantities would have to be correlated with each other. If you make a large enough number of these measurements, you could measure this kind of correlation, and you could test the kinds of hidden variable theories that Einstein had long imagined might restore scientific realism and determinism to quantum mechanics. The first experiments to apply Bell's theorem were performed in the early 1970s, and many variations of these experiments have been conducted since. And the results of these experiments have been clear. Bell's inequality is strongly violated, which means that no combination of hidden variables can even possibly restore determinism or scientific realism to quantum mechanics. Despite Einstein's objections and hopes to the contrary, particles do oftentimes exist in a superposition of states. With the outcome of these experiments, Einstein's dream of a world without chance, and whose reality always exists in a well-defined state, seems to have come to an end. But the failure of hidden variable theories does not necessarily mean that the Copenhagen interpretation of quantum mechanics is true. In 1957, another alternative to the Copenhagen view was proposed, this time by a young physics graduate student named Hugh Everett III. Everett was something of a polymath. He studied chemical engineering in college, and then he went on to study graduate-level mathematics at Princeton, where he focused on the new field of game theory. Then, while still at Princeton, Everett gradually shifted his focus away from math and toward physics, where he became immersed in quantum theory. After he graduated from Princeton, Everett left theoretical physics altogether and instead worked for the Defense Department, where he had a notable career in nuclear weapons research. Everett's work on quantum theory culminated in a paper that was originally entitled Wave Mechanics Without Probability. At some level, Everett's proposal was remarkably simple. Recall that according to the Copenhagen interpretation, a wave function evolves until the thing that it describes is measured, and at that time, the wave function collapses to a single value. This raises the difficult question of why an observation or measurement causes this change. Why does it cause the wave function to collapse? Well, all Everett was really suggesting in his paper was that perhaps wave functions don't collapse at all. To better understand the implications of Everett's proposal, let's consider it within the context of Schrödinger's cat. According to the Copenhagen view of this hypothetical experiment, the apparatus creates a wave function that describes a cat that is in a superposition of both dead and alive states. The cat is both alive and dead at the same time. And Everett would agree about all of this. Where Everett disagrees is in the question of what happens when you open the door to the chamber. According to the Copenhagen view, when the chamber is opened and you observe the cat, the wave function collapses. And afterwards, the cat exists either in an entirely alive or in an entirely dead state. This, of course, squares well with our experience. We don't see a lot of half-alive, half-dead cats walking around. And more generally, we don't witness things that are in a state of quantum superposition. But Everett saw it all differently. According to his interpretation of quantum mechanics, when you open the door of the chamber, the wave function does not collapse. Instead, the world at that point in time is in a superposition of you, the observer, observing an alive cat, and of you, the observer, observing a cat that is dead. So according to Everett's interpretation of quantum mechanics, the world is in a permanent state of quantum superposition, with all possible outcomes fully realized and moving forward through time. For this reason, Everett's interpretation is often called the many worlds interpretation of quantum mechanics. There are a number of things to like about the many worlds interpretation. First of all, there's no special role for the observer, so you don't have to wonder why the act of observation causes a wave function to collapse. And you don't have to wonder what exactly does or doesn't constitute an observer. Personally, I think this is a real problem with the Copenhagen interpretation and a real strength of the many worlds view of quantum mechanics. Furthermore, at least in a sense, there is no longer any role for chance or probability in the many worlds version of quantum mechanics. After the chamber containing Schrödinger's cat is opened, there is a 100% chance that the world will be in a superposition of alive and dead states. It's entirely predictable. Sure, a given observer can't predict whether they will find the cat to be alive or dead, and the outcome that you personally observe still comes down to chance. But from a global perspective, there's no uncertainty in this determination at all. Both outcomes necessarily occur. The role that chance plays in the many worlds view is not in determining how the universe evolves, but in determining which world within the larger universe you will witness and experience. Although Everett's conception of quantum mechanics was very different from anything that Einstein had in mind, I can imagine that Einstein might have been very happy with it. We'll never know for sure what Einstein would have thought about the many worlds interpretation, but it does restore both determinism and a sense of scientific realism to the quantum world. At least initially, Everett's proposal was not received well. Of the minority of physicists that even heard about Everett's work, most tended to dismiss it harshly. But as decades passed, Everett's interpretation became increasingly popular, and now it's a rather mainstream view. But even now, more than half a century later, there is no consensus about whether one should adopt the many worlds interpretation or the Copenhagen interpretation of quantum mechanics. And I don't see this changing anytime soon. The fact is, there is no experiment that could even hypothetically distinguish between these two very different views of quantum mechanics. Both the Copenhagen and many worlds interpretations predict exactly the same outcomes for all possible experiments. No test in a laboratory and no measurement or observation will ever be able to distinguish between these two very different views of the quantum theory. Probably the single most common view of quantum mechanics that is held by physicists is a more practical one, and is sometimes called the shut up and calculate interpretation of quantum mechanics. After all, we know that regardless of whether we adopt the Copenhagen or many worlds interpretation, we'll be able to consistently make accurate and precise predictions. So in this respect, it doesn't matter how quantum mechanics really works. In terms of its predictive power, it just does. So this brings us to the end of our set of 3 lectures on Einstein's role in developing the theory of quantum mechanics and his philosophical and scientific struggles with it. In the next 2 lectures, we'll shift our attention to some of the topics that Einstein investigated in the later years of his life and career.